it's my great pleasure to introduce you today, Professor Chrisley. Professor Chrisley is investigator in signal processing systems for multimedia and bioinformatics. His work on analytics of algorithm concurrently with algorithm architecture co-design has made possible accurate and efficient computations on SoC, cloud, and edge. His work has contributed to more than 130 publications and the invention of more than 50 patents globally. His work on our algorithm architecture co-design resulted in industry development of more than 60 million LCD panels worldwide. 2 patents were licensed to US health industry for the development of analytics platform for prediction medicine products. His work was key in developing international standards like RVC and 3D HEVC through MPEG. Chris was a system architect at Philips Center, project leader in Silicon Valley, was recruited to NCKU in Taiwan in 2003. He received his bachelor from NTU in Taiwan and his master and PhD from UMASS. Chris is associate editor for IEEE transactions on signal processing and was associate editor for the IEEE transactions on circuits and systems for video technology, receiving the Best Editor Award in 2011. Today, he's speaking to us about machine learning for analytics architecture. So it's AI to design AI. Chris, once again, it's a pleasure to have you speaking to us here. Please, the floor is yours.
Thank you very much, Bruno, for the excellent introduction. And it's a great honor, once again, Ricardo, to be invited to this great experience of a virtual EMICRO virtual conference, which is very interesting. And good morning, everyone, also. It's nice to talk to you all, even if I cannot see you all, but I hope you all enjoy. Now, let me try to see. Oh, I cannot. I'm not able to move the slides. Okay.
Sorry, I'm making you presenter. I forgot.
Yes.
Now you can.
Great. Yes. Okay. So I hope you can see the now everybody's talking about AI. I think I would like to share with you what I mean by analytics architecture. And also I would like to have these algorithm and architecture co-design space exploration using machine learning. Okay, and also, if time allows, I'll try to go through some of the case studies, such as, for example, in multimedia, and also in mobile health, which is what we do in convolutional neural network right now. Now, oops, let me try to get used to this. Okay, so yeah. Obviously, I still need to get used to this. Now, we are living in a very vibrant and fast-changing world. So we remember starting from Industry 1.0, where we started having the first industrial revolution. I think there were innovations in energy and electricity, which brought forth automation. Now, we also had revolutionary changes in the traditional artisan craftsmanship, which actually brought forth social, political, and economical perspectives. Now, recently, we see that there is a booming of big data, a lot of information. Now, we are at the stage of Industry 4.0. So if you kind of look around, you will see that McKinsey actually forecasts on changes, which is brought by AI, to be 10 times faster than what we had in the first industrial revolution. And the scope and the scale of the change is about 300 times larger as compared to what we had originally. So we are indeed in a very vibrant and fast-changing world. Now, if we go back a little bit now into history, you see that exactly 50 years ago, you see that, well, 51 years ago to be exact right now, Apollo, actually, we had Neil Armstrong, which set foot on Earth. So he was saying that that was one small step for an engineer and one giant leap for engineering. So you can imagine when Neil Armstrong was stepping onto the moon, he was using one of these computers that is still within the museum of MIT. Now, as far as I'm concerned, this Apollo navigation system is the first navigation system that we have for mankind. Now, you can see that the cell phones that we have are, if not thousands or millions or trillion, a lot of times more complicated and faster than the traditional Apollo navigation computer, which was a little more than half a century ago. And you see that in the middle of this picture that I'm pointing to here, you see that that was actually the computer itself. And to the right here is kind of like the dashboard, the traditional keyboard and the dashboard that we're looking at. And this circuit that we see are actually two NOR gates that we're actually looking at. And these things up here are the copper wires that we have for this computer. Now you see that this is a very, very primitive computer. What we have, even what my teenage son has, is a lot more complicated than this computer itself. But imagine, how was it possible for mankind to be able to use this primitive computer to set foot on the moon? I think I personally was thinking that this was because we were actually able to have computers, circuits, and also together with algorithm. So math was a very important thing. So you see that it was one of the professor, Kalman, who was actually attending a conference very much similar to what we are doing right now in Florida. He was teaching in the University of Florida, and he was going to a conference, and he met a Russian mathematician, and together they invented Kalman filter, which was then substantial in actually putting Neil Armstrong and putting mankind on Earth. That was really inspiring for me. So I think a lot of my work was then gearing towards, so you see that that was the computing platform that we have. So as we grow more and more, you see that we are reaching out even further with Internet of Things and going even deeper. So to the left up here, you see that all these systems are being connected in IoT, and we see that we have chips everywhere. Okay, this is not the methanol chips, but the ICs that we have, especially in circuit systems, in microelectronics that we have. Now, if we go deeper, so into the human brain, we see that these are neurons, and also we see the genes. So you can imagine that the data is getting bigger and bigger. So, yeah. So if we look at the big data landscape, people were saying that we're at the age also of the big data. You see that for the efficient gain and the business value that we have, we see that, okay, from the x-axis, we see that these are the gains of AI as a share of total from data analytics. And this is actually the gains from AI in billions. So we at the advanced electronics and semiconductor is about here, right? So Gartner also was saying that what we have actually is either assisted or augmented intelligence, and these actually will create 2.9 trillion business values. Okay. Right, so you see that we also have, we see that the platform gets to be more and more complicated, and the data gets to be larger. Now the algorithm also should is also more complicated, more complex. Traditionally, people were talking about analytics algorithm, where they analyze the speech and all these images. It was like 10, 20 years ago, this was advanced research. They were trying to do speech recognition with feelings. Now they were also trying to do image recognition, say for example, facial recognition with emotion also, as we can see this very, very happy and bright young lady in the middle here. But what do? I try to analyze the algorithm, or to be exact, I analyze the data flow so that I will be able to map this data flow onto an architecture in a very smart way. So in essence, I also have a cloud that actually thinks, because this is what we call analytics architecture, and something that will actually adapt itself to the complexity of the algorithm. So I think Amazon was talking about AWS, and in 2018, Microsoft was talking about build 2018. So that was the intelligent cloud and intelligent edge that they were talking about. But I started actually working on this many years ahead. So we had actually our technology also licensed by people in the year 2015, based on analytics architecture, if you can see. Yes. Okay. Okay. So we started actually trying to let me try to close my camera here. I think there has been delays. Yes. Thanks, Bruno. So this brings us to what I call the architecture algorithm co-design, because I'm doing analytics architecture so that I can have smart system on a chips, smart SoCs that we see here. Okay, so if we all remember, when I was in a conference in year 2014, I met one of my friends from ETHC, and I was telling him that, hey, Nicholas Wirth in 1975 was saying that programming is actually equal to algorithm plus data structure. So I was very much inspired by this. So I was saying, hey, because design here means system design, is actually equal to algorithm plus architecture. So my friend was saying that, hey, I couldn't agree with you more. And he was telling me that Nicholas Wirth is still around. He's still having coffee with my friend. Is still in Zurich right now. Yeah. Okay, so if we start looking at these, systems here, you see that if I look at the platforms now, Professor Wayne Wolf, or now Professor Marilyn Wolf, when he was in Princeton, he wrote a book on SoC design. So he was writing the slides on writing the two axes, performance per unit area, which is, and also the power. So I added this axis, the z-axis on flexibility. So if you look at all the platforms that we have right now, if you kind of look through them, you see that we have the traditional general purpose CPU, which is purely software. Now you see that it is very flexible, but at the same time, it consumes a lot of power. And you can see that if we try to look at the speed, which is what I mean by performance here per unit area, it is very low speed. And on the other end of the spectrum, we see that we started having ASIC design. A lot of these hardware, digital hardware design that we started having, you see that the performance per unit area was very high. And also, at the same time, the power is also very low. But you can see that there is also a limitation in terms of the flexibility. So whenever you tape out something, you need to be able to change that. You need to be able, whenever you want to change an algorithm, if you stick with hardware design, you have to be able to tape out again. So that was not favorable. That's why people are looking at application-specific instructions at FPGAs. So FPGAs. So end of last year, Xilinx was also announcing their multi-million gate FPGAs, which is in between some of these. Now we also were looking at recently embedded multi-core processors. So you see that we have been going through many of these. So beyond cloud, Moore's law doesn't work anymore since 2013. So we can actually see that. In addition to that, we're also going now towards the other end, which is the cloud and heterogeneous system. So that was the IoT, which is going to be able to be more flexible, is larger power. But if we go deeper on the other end, we also look at the neuromorphic devices that we see, because at some of the times we don't care about the accuracy, but we want to be more efficient. We want to be faster. And also at the same time, we want to be also having lower power. So if we look again and look at the smart computing that we were talking about, we see that the human brain is actually the most powerful, the most power efficient intelligence that we have. When AlphaGo was competing with Lucido, you see that even if AlphaGo was fast, it was taking 3,000 million joules of power. But at the same time, a human, the chess king of Korea, Lucido, was actually taking only 10 million joules. So the human brain is 300 times more powerful and more efficient. So now, when we design things, we like to have high speed, high accuracy, especially also low power. So all these will come if we look together from the very beginning in doing a top-down design, as we were saying. Okay. So if you look in the traditional design, okay, we have design which goes from algorithm design directly to architecture. But now we have many chips that fail. When I first came back to Taiwan, after working as a system architect in a former Philactor, I was telling them that I am who came back from the dark side of the world. So meaning that we have failed a couple of times because the chip for Trimedia, actually TM2 was really not that successful, because once we map the algorithm over to the architecture, okay, and if the architecture doesn't work, we didn't have a back annotating mechanism. So from experience, we were knowing that we need to have software, hardware ingredients, okay? We need to understand a lot of these at the algorithmic level, from the very top level, and we need to extract the complexity features from data flow graphs. And the complexity measures are actually the number of operations, the degree of parallelism, the data transfer rates, and the data storage requirements. So these are actually similar to the features that we are extracting. So at the same time, if the algorithm doesn't work, we will have back annotation, which feeds back everything. So this is the idea of algorithm architecture co-design that we have here. Okay. Now, so if we look at this, we see that traditionally, what we have is the algorithmic space. And then we see that the applications that we have may be IoT, mobile device communication in 5G, and also multimedia applications, biomedical applications. Now, most people are very much interested in the deep learning for different applications. Now, traditionally, we see the software-hardware co-design or co-exploration space. So my contribution after coming back to academia is to introduce this part, which is called the algorithm architecture co-exploration space, in which I model. Okay, so when I study the algorithmic space, we try to model this using data flow graphs. From data flow graphs, we use spectrograph theory to extract features in a way similar to the feature extraction in machine learning. So we are actually doing feature extraction using eigen decomposition, as I will explain. Now, if we look at these architecture and we know the complexity, which are the features, and we try to then go to software-hardware co-design. Now, I'm also adding going directly from also to neuromorphic. So if this data flow model doesn't fit, we very much similar to the cross-level design, we try to back annotate to upper level, back annotate to go back to the algorithmic space, so that the algorithms should fit into the target's architecture platform. Now, as I was saying, we can, from this information, we can study the parallel architecture or the reconfigurable architecture that we have and go into the traditional software-hardware co-design, in which we can do software-hardware partitioning, so that we can either do things on CPU design or FPGA or ASIC, customized logic, which is ASIC, to do hardware accelerator. Now, I am also collaborating with one of my young colleagues who came back from UC Berkeley, working on neuromorphic computing. So using the data flow model, we can also map things. I'm sure also many of these people working on neuromorphics can also go from the system level directly into the circuit level, or the circuit and device level, where they have the neuromorphic accelerator, which is using memory device, which is for TCAP, or the quantum simulator that they actually have. At the same time, so if things don't work, whenever we have cross-level of abstraction design, we also back annotate things. Now, people are also in the industry, I'm sure, going through the circuit and device co-exploration. So these are things that we're also looking at. So we are actually dividing the level of abstraction in many layers and trying to do cross-level of abstraction, which is what we have been doing for the last 20 years, and which is what I believe to be the future of design. Yes, right. So now the trick is, when I was looking at what MIT's signal processing lab was doing, when they were trying to model system, they're still using the traditional linear difference equation if they have digital side, and they were also using the traditional Laplace transform if they go for the analog. But now, in order to look at and to explore the algorithm and architecture co-design space, we are trying to look at different data flow models. Now, when I look at the algorithm, what I mean is the traditional algorithms, as was the computational model, as was defined by MIT. But we are to also on the data flow using something similar to the signal flow graph. Now, these data flow models are modeled using graphs, and these actually can model the potential anticipated computational platform better. So this is the trick to what we have been doing in terms of, so once I model the data flow graph using stochastic process, then I will actually be able to use machine learning to extract features from the data flow graph so that I will be able to do algorithm architecture co-design space using machine learning. So that is the main trick that we have been trying to do. So as you can see, I'm just going to go through things very fast and tell people what we mean. Okay, let me try to go to the other slide. So let's go back to the signals and systems, or the signal to system class, or the digital signal processing that we have. On the top, you see that we have an algorithm, which is just a 3-tap FIR filter, while n is equal to, and I have shown the data flow or the block diagram, which is the data flow graph for the direct form, as you can see. And the transpose form, which is also called the data broadcasting form, is shown at the lower part here. Now, because of time, I will not bother you too much with the things down here. We kind of have a pipeline view of data flow in the FIR, in the direct form. You see that if I have xn, which is the input here, for the direct form, we actually have the data flowing through, and it will first be latched by the flip-flop or the delay here, and then it will be latched here. And the A0, A1, and A2, the D actually stand for the registers, and D0, A0, A1, and A2 actually stands for the multipliers. So when I add them all together, this is the add here actually represents the adder. So I'm not going to go through the graph below, okay? But as you can see, now what I have for the if I have x of n, which is equal to 8 bits. Now, when I have the direct form, you see that I need to have 8 bits to save this data. Now, the second register is also 8 bits. Now, if this 8 bits is being multiplied by the first multiplier, if it's also 8 bits coefficient, the output, the data path that I have here should also be 16 bits when I do the multiplication. And after addition, it's just 1 extra bit. So this is also 8 bits, so this should be 17 bits. Now this is, if I look at the physical thing of what I have here. Now, if I look at the, transpose form, and I don't have time to go through every detail, but you see that it is being broadcast. An 8-bit input will be broadcast to all 3 multipliers. And the numbers, after I do the multiplication, this is 8 bits. This is 16 bits because 8 bits is multiplied by 8 bits. So they will be saved. So the register I need is 16 bits. And then this is also 16 bits. So here in the second register in D1 that I have here, I need to have a 17-bit register. So you see that after multiplication, all these data paths also blows up. They go up to 16 bits. Now we see that this is just a very, very simple example. If I am trying to implement this algorithm, which is just a very simple FIR, free-tap FIR filter. If I am able to, if I want to implement this using embedded software, I need to have the GPU or the CPU, which is capable of having this is 17 bits, and this is 16 bits register, which is more power. And also, the wires are wider. I also need to have a broader data path over here. So we can actually see that most of the power that we have in hardware and also within embedded software is from data movement or data transfer. So a lot of power will be burned here. In addition, we also will have a lot more power when we compare with this 16 bits and also 17 bits register, as opposed to the two 8-bit registers that we have. Now, please understand that I'm only doing data flow modeling here. I have not implemented any embedded software, nor have I done any hardware design. But I am already able to, at this level, try to map this top level algorithm potentially to architecture. So the idea of this is to be able to extract features, to know the number of operations, to know the data transfer rate, to know the data storage requirement that we have. Yes, and so, or is there any possible ways of parallelism? So from here, we see that we need to have the number of registers that we have here. We need to have 3 multipliers and 2 adders. And we also will be able to see the data storage requirement that we have here. So all these features can actually be extracted from the data flow models. And I have not written any embedded software or design or did any RTL design yet. But all these information needs to be known from the very early stage of design that we actually have. And this is facilitated by the data flow modeling that we actually have. So the data flow model actually help us cross from the algorithm to the architecture level, which will then be mapped to the embedded software or also the hardware after doing software-hardware partition. So, if we were doing hardware, we're just synthesizing results for the free-tap FIR filters using direct and transpose form. As you can see, for the direct form, we have a shorter critical path. We have a longer critical path. So the timing is longer. Now for the transpose form, because the registers actually broke the critical path, so the timing will be shorter. So I can synthesize this to be a faster speed. But the cost that I have for a faster speed is always a trade-off in the gate count or the area that we actually have here. And of course, we see that another trade-off that we have for timing is also 37, which is a higher power that we see here. So you can see that all these information can be actually seen or extracted very early on after we study the data flow model, as I have demonstrated here. So this is why we are trying to model the computational platform using using data flow models. And once again, if I have the data flow graphs, okay, now these graphs could also be could also be modeled using stochastic process. So then, because the data flow model actually maps a different instantiation, architecture or hardware instantiation of the algorithm, I call different data flow models different architecture instantiation of the architecture, which is the computational model. Now, so since the data flow model connects the algorithm and architecture, and if I model that data flow model using stochastic process, then I can actually extract features and do machine learning tricks so that I am able to design a very intelligent platform, which is modeled by the data flow graph. Yes. So, so then the question is, now one of the things that happened when I was a system architect in former Philips Semiconductor is that sometimes the algorithm is too complicated, and no matter what we do, it is hard for us to map onto either one of the platforms that I was showing you. Now, so the question is, the key thing is, how big is big? How complex is the algorithm? So the complexity are actually the features which I extract from the data flow model, which actually characterizes the data flow models. Now, one of the things is that when I model these data flow models or different architecture instantiations, they are actually representing algorithmic intrinsic properties. And I need to be platform independent. Because if I, say, for example, have a platform even with different DRAMs, say if I have a DRAM from Samsung and another DRAM from Micron or DDR, now the timing or the cross-page reference will be different. So that will actually give us a different platform. So the data transfer rate, data movement will be different. So these numbers cannot be used in the very beginning when characterizing or featurizing the complexity model of the algorithm. So I actually have many different data flow models or different instantiations or realization when I study different data flow models of the algorithm. Now there are a lot of data flow models, but isn't this what AI is good for? Now, when I say AI, I am not talking about artificial intelligence. I think artificial intelligence is more of a marketing word. I use AI as augmented intelligence because the design space, the algorithmic and architecture co-design space is so large that to find a specific solution which is good for the specification that I have to design the system, I need to optimize this. So I am exploring the algorithmic and architecture co-design space using machine learning algorithms, because that is exactly what augmented intelligence is, to speed things up, to speed things up for human. So the features that I try to extract from the data flow models or the complexity so that I have a good understanding of the algorithm is first, of course, the number of operations. I try to break them also into addition, subtraction, multiplication, division, and also shift and logic operators. Now, in the traditional complexity thing that we learn in computer algorithm, where we use execution time or order of growth, in the book that we also have from MIT, you see that that was an ideal case where the execution time was the same for different instructions. It was at the instruction level, but you see that addition and subtraction is actually faster than multiplication, and division is also slower than multiplication. Of course, shift and logic operators should be a lot slower than division and also multiplication. But trying to model the complexity using execution time at the instruction level, and the instruction time for every instruction to be the same for addition, multiplication, and division for each of the instruction is not accurate enough. And also, it will be different for different architectures, because for parallel computers, if I have traditional SIMD, or if I have different issue slots for, say, for example, TIDSP, then the same instruction will not be equivalent to the same instruction that we have in a RISC machine, for example. So the traditional complexity measure, I'm not saying that is wrong, but as far as what we are concerned, that was considering that we have an ideal platform. But now we don't know the platform. We need to design the platform, whether it is on software, hardware, or IoT, or neuromorphic systems that we have. So that's why we go to the number of operations, as I was saying. And we also have to look, of course, into the accuracy that we are looking at here. Now, the second thing that we are trying to look at is the parallel, the intelligent, parallel, and reconfigurable computing, okay, based on spectrograph theory. So as I was saying, now if you can imagine, I just remember when I was in college, and I was also teaching the signals and systems class. Now, you can think of parallel computing as the forward transform of what I'm setting up. Now, I'm thinking of what we have in Fourier transform. Now, when we have Fourier transform, in the analysis equation, when we analyze the signal, we're actually able to transform that into the frequency space so that we understand what kind of frequency components we have. Say, for example, if we try to differentiate or do AI for recognizing between male and female, we can see that the feature that we have for female is with higher frequency components. Now, that is the analytical equation. Now, if we go back, a lot of these machines can have syntactic sounds. So if we have the synthesis equation for the Fourier series or for the Fourier transform, we'll actually be able to synthesize digital sounds or audio that we have. Now, in a manner similar to the Fourier transform, I have formulated this problem to analyze the parallel computing. So I am modeling every processing element to be a node, and the data between these processing elements to be the edge. Now, so if I have parallel computing, it is similar to mapping. Now, one of the ideas of parallel computing is to be able to now parallel computing happens if there is no dependency between the processing elements. So if I am able to transform the original, if you look at A here, the graph, into disconnected components, then I know that in B here, all these three components after transform can be performed in parallel. So if I am able to model this using data flow graphs and to use graph theory, spectral graph theory to come up with this, then this could be a retargetable compiler that we have. Now, traditionally, you see that I have the source code and I have a compiler, and then I go into the assembly code. Now, if I know the source code and I have a retargetable compiler, so after using the analytical software that we have, you can, if you know also the processing model, then you can actually put this, you can actually use this platform more efficiently. Say, for example, if I have a GPU which has 256 cores, for example. Now, if my, after analysis, I know that I need, say, for example, only 128, I can then turn the other 128 cores off so that I can have low power. So this will not only speed up my my computation, because of parallel computing, I will actually also be able to have low power. So I could also put this onto the cloud. So on the multi-core, each of the processing element could be a core, or they could be a computing cluster. Now, using the same thing, using graph theory. Now, each of this cluster that I have here could be decimated to different clouds. Say, for example, if I have a cloud in Brazil, I have a cloud in Taiwan, and I have another cloud in the United States. So this can be dispatched on different physical locations, depending on the traffic also, to come up with a very efficient and flexible cognitive cloud, if you would. Now, when we are doing this, why do we say that this is machine learning? Because, well, so if you also, so what I'm doing is using spectrograph theory in exploring the algorithmic and architecture co-design space. Now, you see that originally the connected components of graph are eigen-decomposed, where the spectrum of the unconnected graphs serve as information or features which are extracted. So this is the feature extraction of the machine learning part. Now the decision making part comes from the bipartite or k-partitioning when I use graph theory, because you see that when I use the principal axis theorem, when I try to rotate the axis into another space so that there is no dependency between the clusters. So I am breaking this link between this cluster and this cluster. This link has been broken. So I am trying to use independent. So I'm making these independent so that I can achieve parallel computing. I think this is the main idea. Yeah, this is the main idea. So okay, so I am actually giving you an example here. This is a graph, and this is the adjacency matrix. These are the matrix that we have. And the Laplacian matrix is the L, which is equal to the diagonal of the matrix multiplied minus A. Yeah, I think when the slides were being taken into the PD map, they had a lot of things which didn't come out. So you see that these were actually, this is actually the Laplacian matrix. Okay. Now if I take the do eigen decomposition. Okay. So wow. Okay. This is I apologize for the effect. The effect of these this transmission here. So you see that for degree of parallelism, I do eigen analysis of the graph. So we started out with output 1 and output 2, and this is the data flow diagram, and this is the causation graph that we actually have. Now this is the Laplacian matrix that you see. So when I try to do eigen decomposition, I try to find the eigenvalues. Now the eigenvalues that correspond, so you see that this is A1, B1, C1, D1. So if this is a node, and this is a node, and these are actually the edges that I have, I can actually label these nodes in a random manner because in incident matrix and linear algebra, it doesn't matter. So I have 1, 2, 3, 4, 5, 6, which are the causation graph. So using this graph, I have a Laplacian matrix. Now, after taking the eigenvalue, an eigenvector, you see that the eigenvalues, which is the feature that we try to find, is to look for the eigenvalue which are equal to 0. Now, the eigenvector corresponding to them should be disconnected. So you see that for eigenvalue 0, this is the eigenvector. This is a node 1, which is node 1. This is node 2, and this is node 6. Node 1, node 2, and node 6. This is eigenvalue 0. This is also node 3, node 4, and node 5. 3, 4, 5. So these two eigenvectors are linearly, they're actually independent of each other. So that tells me that if I had this graph, then I'm able to do these two components in parallel. So the degree of parallelism can also be quantified. I say that this is 2 times the 2 times this. So the degree of parallelism is 2. Now, since these two graphs are also of the same size, we say that this is homogeneous. Of course, when we do this eigendecomposition, this also gives me instruction to study the instruction set architecture design for the overall platform. It could be SOC. It could also be the cloud or the IoT system that we are actually looking at. So that was pretty much the parallel part. Now, if we go back to the synthesis equation, you can see that we have reconfigurable computing, which is very similar to the inverse transform that we have. Now, when we look at the reconfigurable computing, what we normally do is we try to find the commonality within the data flow graphs. Now, all these common graphs can be reused when I try to synthesize or reconfigure the platform for computation. Say, for example, for the CNN computational platform here. So we have been, we're trying to use the traditional multimedia case that we see. We have a reconfigurable architecture, which is trying to extract the commonality extraction from the. So in MPEG-4, we see that we need to calculate this filter here. And for H.264, this is the filter that we have. So if we divide everything by 8, and you see that I have this blue I to be shifted by I, and the white I to be right shift by I, and this plus is the addition here. So in order to implement this filter over here, you see that I can have x0 and x7 here. So I can just add them together because it's a 1. Of course, later on, I have to subtract this. Now, for 3 and 3, now normally in hardware design, or even if you want to do hardware design, we would like to have 1 and 6 here, but this is not 2 to the nth power. So we try to shift, left shift by 1, which is multiplication by 2, and then add 1 to it, which is kind of like a mux, which we do. And then this will be equivalent to a multiplication of 3 when we do this. So when we add everything together in a similar way, we do that for -6 and also 20. So in order to come up with MPEG-4, this is what we have here. Now, in a similar manner, if I have ABC H.264 and also these coefficients that we have, you see that the data flow graph is the same whether I have the brown part for MPEG-4 and also the brown part for H.264 or ABC, and also this part that I have for MPEG-2 and ABC. So I can actually design a hardware or embedded software which calculates these common parts. So when I really need to calculate them, I compare the commonality between each and every one of them. So, okay. So if you look at the bottom here, I really hope I could have that's why I had the slides. I didn't put up the PDF here. Okay. So that's why you see that if I have the MPEG-4 here, I need to have module 0, module 1, module 2, module 3, and I need to use all of them. But if I need to do this, say for example for ABC, these two modules can be bypassed. All I need to do is to reconfigure or to synthesize module 2 and module 3 and bypass module 4. So I'm actually able to have multi-purpose multimedia, say for example, decoders here. Now I can actually look at the commonalities and try to reconfigure them, reconfigure the common parts so that I can reuse them. So this can actually save a lot of power and also save a lot of circuits. Now in a manner similar, we're also using this for CNN here. Now you see that for CNN, for the convolution neural network, we actually do a lot of convolution, as you can see. Now, in addition to the convolution, we also try to look for principal component analysis. So we transform all these convolution using principal component analysis to extract the commonality. Now, at the same time, you see that after transformation, there will be a higher symmetry that you see. So there will be 4 different kinds of commonalities or 4 different kinds of patterns. Now, there will be, if I use the 7x7 convolution in CNN, you see that I have, I actually will have 16 filters. Now, each of them will have a higher degree of symmetry, as you can see here. So each of these is the first pattern. Each of these filters are the second pattern, the fourth pattern, the third pattern, and the fourth pattern. So you see that if we look at this filter here, which is after transform, there will be more. We will see that there will be more symmetry. Now we see that we have more even point symmetry, odd vertical symmetry, and also different kind of symmetries that we have here. I apologize again because of PDF conversion. A lot of these motion pictures that I have has been taken out. So I think the key idea is that for each of the 4 patterns, we see that these commonalities are actually higher. So if I have more commonality, I can do less computation. So I have fewer circuits, and I can have a lower power. That is the idea that we are trying to explore. So when we also do the feature extraction, now we have also proved that by using features which is closer to the original experts. So I'm trying to give everybody information here. I think I will skip the multimedia part, but even if you can see, using AAC for the spatial temporal recursive estimator that we had, we were comparing this to what NTT Docomo had many years ago. Now, for the same resolution and search range, the PSNR that we had for our algorithm for the 3D recursive was 35.45 dB. Now, the total gate count that we had was more than 10 times less than what they had. And this was made possible because of algorithm architecture co-design, which was what we did quite a few years back, more than 10 years ago. Now, we're applying algorithm architecture co-design again to, I think my time is up, so I'm speeding up here as everyone can see. So we see that one of the points I'm trying to make here is that if I have all the data in the world when I do the training, then all these features will be updated. So if I have a lot of data here, but now in a lot of applications, since I do not have enough data, so what we do is we have started out using features, handcrafted features, extracted, and insert them into the first and second layers, so that okay, sure, that would be great. So that we can have all these so because I don't have enough data here in most of the real world scenarios, so we will be able to then put, say, the handcrafted features, say for example Gabor filters that we have. So for the Gabor filters, you see that we were trying to extract features, which was, this is the, these are the medical images for skin to understand the melasma from a very high frequency laser, which penetrates the skin. So we see that this is the normal image. Now you see that they start having dendrites, which extends out at different directions. So these are real world images that we actually see here. So we were principal analysis. We were using a filter to extract these features to quantify their direction. So you see that the more directions there are, the better, which is according to the pathology information as was characterized by the medical doctors. We work with National Taiwan University, my friends also. So you see that these are the features at a 0 degree direction. These are the collagen fiber, if you or the direction that we have in the 45 degrees, 90 degrees, and 135 degrees. And all these are showing up. And these are the different things which are combined together. So we are actually doing real world images. So by taking handcrafted images, features, we're actually able to converge faster. And the accuracy will actually be able to be sustained. At the same time, if we were to implement this in the hardware side, you see that because after Gabor transform, the filter is actually having Gabor filters actually having higher degree symmetry, as you can see. This is the original filter. This is after Gabor, after principal component analysis. This is also another filter. This is after the second Gabor. So you see that there will be higher degree of symmetry, as we were explaining just now. So if we do that, we see
Chris, your microphone is off at slide 43.
Chris, we have no sound from your side. It seems that your phone should be on, but there's no sound coming. Pessoal, a gente está tendo alguma dificuldade. Aparentemente o áudio do Chris não está chegando até nós. O pessoal está tentando arrumar esse problema aqui.
A gente está conversando com ele pelo chat aqui, mas ele não leu ainda. Eu acho que acidentalmente ele deve ter desligado o microfone, né? Porque ele continua no ar, como vocês podem ver aqui pelo cursor no slide que ele está passando, mas ele não se deu conta ainda que o microfone foi desligado do lado dele aí, né?
Parece que ele pode não estar nos ouvindo.
Não, ele não está nos ouvindo também. O áudio dele foi desligado, né? Mas ele vai se dar conta daqui a pouco aí, que vai ler no chat as mensagens que a gente mandou para ele, né? Então, só um pouquinho de paciência aí que... Enquanto isso, já pode ir fazendo pergunta aí pelo canal do YouTube, né? Que o Bruno Zatti, que está coordenando a sessão, depois vai...
As perguntas podem ser feitas em português sem problemas, tá, pessoal? Ou espanhol, eu vejo que tem pessoas de outros países que eu faço a tradução aqui para o Cris, não tem nenhum problema.
Se quiserem fazer em francês, eu também traduzo. O Rafael. Bom. E desculpe aí também por uns probleminhas da conversão do PDF aí, que ontem eu testei com ele lá tudo, a gente passamos até um certo quantidade de slides no início que não tinha problema nenhum, e foi falha nossa de não verificar todos os slides aí na conversão do PowerPoint dele para o PDF, né? Bom,
pessoal, vocês podem ir fazendo perguntas de vocês já ali, viu? Colocando nos comentários ali no YouTube, que eu já posso ir selecionando algumas perguntas.
E naturalmente nós vamos começar a sessão do sim um pouquinho mais tarde, né? Mas nós temos tempo suficiente para isso, né?
properly now? Sorry, I disconnected my microphone.
Okay, yes.
Now
Yeah.
we have you once
Yeah.
again. We missed you actually in the slide number 43. It would be very kind from your side if you could go again through your conclusions.
Right. Okay.
From slide 43.
Right. So should I go back to 43 or go to 45?
Yes, if you
43
can,
is perfect.
be great.
Sorry, I disconnected my microphone.
Okay, yes.
Now
Yeah.
we have you once
Yeah.
again. We missed you actually in the slide number 43. It would be very kind from your side if you could go again through your conclusions.
Right. Okay.
From slide 43.
Right. So should I go back to? Okay. So if you see that when I try to do principal component analysis and I try to take handcrafted Gabor features on the convolution neural network, what you see is that due to the higher symmetry, the number of operations or the number of additions that I have, if you can see, for the Gabor filter bank, which is the handcrafted features that I extracted for the convolution neural network, for the analysis of the medical image that I was doing, dropped from 200 million to 72 million. And the number of multiplications dropped from 205 million to 60 million. So this is actually the power of algorithm and architecture co-design using the using machine learning, which is what we were talking about. So in conclusion, when we design systems, you see that we need to do cross-level of abstraction designs, which includes algorithm and architecture. So if you remember, we are modeling the computational platform using data flow graphs, which connects, which maps the algorithm onto the architecture platform. Now, I am trying to explore the co-design space, algorithm architecture co-design space, using machine learning. And hence, that's why we say that this is machine learning for analytics architecture, because what we were doing was analytics architecture. Now, this is AI to design AI. Now, we are also, as you can see, providing flexible, high accuracy, high efficiency, low power, and also low cost design. So when I first came back to Taiwan, one of my friends in the industry had collaboration with me. So we were trying to design something which needs to be also very cheap, because you need to have low complexity, very high quality system designs. But you cannot, you have to be very low cost, because most of what we had was being sold to, say, for example, Asia, including, for example, China. And so our quality was was good. At the same time, we also have low costs. This was made possible by the AAC methodology, which was adopted. And my friend and I had been very successful in deploying 50 million units. Now, this was last year. So you see that this year they were saying that we have been selling more than 60 million units of LCD panels worldwide, which is designed based on this AAC, or the machine learning for analytics architecture, which includes cross-level of abstraction framework. Okay. Now, when I was talking about the cloud platform, because of time, I talked only about the reconfigurable and parallel part. Now, if we were to analyze the data transfer rate in addition to the data storage, that would bring us to not only 5G platform in communication, but also 6G or beyond. So this actually facilitates us with a methodology to solve cross-disciplinary problems in smart manners. Should we if we remember, starting from Neil Armstrong, we were going for the last 50 years. Would this methodology actually bring us to another 50 years ahead that we're projecting? Okay, so coming back to what we had, I remember when we were in college, a lot of us wanted to go to the United States to study. So we were very, especially in the Department of Electrical Engineering, we like to have computers, communication, and control. So we have 3C. Now we have 5C. The other 2C's being car, autonomous car, such as, for example, Elon Musk, and also care for healthcare. With that, I think that will conclude my presentation today, and I am opening to questions right now from the audience. Thank you.
Well, thank you so much, Professor Lee. It was a great talk. Please, if you could just open your camera and
yes,
follow you during this question and answer. I have a few questions, but I'll probably go directly to questions that have been made by others.
Okay.
So I start here with Professor Fábio Ramos from the Federal University of Pampa. I would simplify the name, and he asks about the applications that you understand are more suitable for using your approach. Is there a specific niche of application, or do you see it as more like a general sort of solution?
I think it's more of a general solution. So I was trying to take different examples. So I was using multimedia and also biomedical. Yes, it is this is a general methodology. Yes.
Okay, perfect. Another question from Claudio. It's regarding if you understand it to be possible to observe the behavior of one given system or one given algorithm or set of algorithms and use machine learning to train a system able to model such complex systems. I mean, is it possible to train a machine learning based solution to model these specific systems or algorithms?
That could also be possible, right? Because once you have the data flow graph, so you can do many things to it, including a neural network. But the trick is, if you want to train, the reason why I didn't use that is because when you do training, you need to have data. So you don't have sufficient data, then your training will not be in an optimal design. So that's why I went back to the traditional machine learning method of doing feature extraction using spectrograph theory, and then optimization using bipartite theory in graph theory. So I think, yes, it is possible, but the data is the problem, right?
Yeah, it seems data is always the challenge, right?
Yes.
Professor Suzin from the Federal University of Rio Grande do Sul is making a question here. He understands you have presented a very simple example using the FIR filter with, I think, 2 or 3 taps. What would happen I think the question is more in the direction of how your system behaves if you have a more complex example, like with 100 taps. Would it answer you, okay, I have a very long circuit path, or it's more like it's going to propose different ways to deal with that? So for more complicated examples, how your system would behave?
Yes, I think that is an excellent question. Now, I think, first of all, some of my slides were taken out. So I was, one of the slides that was taken out was the graph. So the chart that I drew was to help users understand the flow of the data through different hardware. on the platform for the two realizations or implementation of the FIR filter. Now, if the algorithm gets to be very complicated, we try to use graphs. So when we use graphs, then the limitation would be on the number of nodes or the number of nodes that we can actually model. So that will actually be scaling up with the complexity of the algorithm. But then, since we have cloud right now, so that, we have seen researchers trying to do like more than 10,000 nodes for the graphs. So now with all these computers, especially cloud, we can do many nodes, multiple tens of thousands, or even up to millions of nodes. So that will be a super graph. I hate to say this, but my friend in Microsoft is also doing something similar.
Certainly, it's such an interesting challenge that certainly more people are trying to solve these sort of questions also. If you allow me, I will have one question. You mentioned, especially in this cloud context, there's a lot of so many challenges related to communication, actually. So how this system can model and understand the communication delays or communication overhead that you may have?
Yes, we actually have that for graph theory also, right? We also have another part on the data transfer rates. Yes. And we were also trying to use graphs, we were trying to model the also the overlap and data reuse using the lifetime of the data. All these information are extracted from the data flow graphs also.
So you have sort of complementary graphs, one for the processing and one for the communication.
We model everything on the graph, on the platform, but we use the edges to model the data transfer. Right, so that will be modeling, I hate to call it the bandwidth, because if I use bandwidth, then it will be platform dependent. So I try to model the edges, and I use graphs to understand the cut sets of different edges, which will then estimate the data transfer rate, which is platform independent.
Perfect. Perfect. I think it's clear. One last question from the audience. It's regarding also from Professor Suzin from UFRGS. He's asking about the possibility to use AI. I don't know here if he intends to use artificial or augmented intelligence as you defined, but it's his question is, how about using AI, and what are the challenges related to using AI to specify architectures at high level? I think it's a very general question.
What at the high level, sorry? To specify what?
Architecture specification.
Oh, I think this is exactly the idea, because I am actually using augmented intelligence, as you can see, because this is the key essence of what we have. So we started out actually from the traditional profiling, which is software-hardware co-design or software-hardware partitioning. But now you see that if I model the algorithms using different architecture instantiations, now each of the different architecture instantiation is a data flow graph, which is equivalent to the realization or implementation that we study in DSP or signals and system. Now, so we are actually using AI to select different data flow graphs as we were representing. So in that sense, so I think what the professor asked is an excellent question. When I am doing design space acceleration, which is enhanced in speed by the augmented intelligence, that is exactly what we were trying to use to help, which is similar to the traditional profiling in hardware software partitioning in the traditional design for architects when we are trying to do specification. That is exactly, this professor hit the point exactly. That is an excellent question. That is the key to my talk today. Yes.
Sounds great. I would expect great question from Professor Susi. He's a mentor for us in South Brazil, I'd say.
Yes.
So, Professor Chris, we have nearly more actually than 200 people watching you from all, mostly from South Brazil, but I was checking who was attending, and we have people from all over Brazil and people also from other countries. I've seen Colombia and Spain at least. So it was a pleasure to have you here. We definitely, but I'm afraid we have no more time for keep talking. But we hope to have you here next time personally in South Brazil. And once again, the name of the EMICRO organization, I would like to thank you so much for taking your time, especially during night. And so instead of resting, you are talking to us. It was a great pleasure. So thank you so much once again.
Thank you so much, and thank you to all the audiences who have been here. It was a great pleasure.